I spent the first 9 years of my career at Google, which was probably about 8.5 years longer than I thought I was going to stay there after my first week. Um, but I ultimately got a lot out of it and really enjoyed the work I was doing there. This talk is probably a lot closer to the work I was doing at Google than the work I'm doing now, which is why I mentioned the Google thing in the first place. I built big distributed systems at Google, and now I'm working on big psychosocial systems at this startup called Matter, not to be confused with the Medium magazine called Matter or the other startup called Matter that I'm incredibly irritated about. But we're building something that I think is pretty interesting and special for that's sort of designed to be an antidote to social media, which is a plague. Okay, so anyway, this is going to be a short talk because that's how it is. I'm going to try really hard not to rehash what's in some really excellent talks that you can read slides for online. Rob Pike has given incredible talks on concurrency. I will not be trying to cover that material. I will try to get a couple of nuggets through, hopefully, that are interesting to people and something that you enjoy thinking about and maybe are novel. That's really what I'm aiming to do. And if, again, anyone wants to talk about this stuff, send me an email or talk to me afterwards, and I'll try to stay for a while. I love talking to people. All right, so healthy distributed systems. I think it would be good to start by talking about just my kind of reflections, having spent a long time at Google working with distributed systems, what I really like to see in them. The first thing is I like the high order bits to be right. I don't really care that much about the incredible details, especially for things like throughput. Like if you spend 9 months tuning your throughput into oblivion, it's likely that by the time you're done, hardware will have gotten faster than whatever improvement you made in that 9 months. It's just, I think it's really smart to think about the high order bits of performance. Definitely you want to be within order of magnitude of what should be possible by the raw numbers. I also think it's important to get the shape of the system right. I think it's incredibly important to be able to build systems out of small composable pieces and not these monolithic things. Go does great on both of these fronts, especially in the latter. I think in Go it feels somehow very stress-free to me to build a new process in Go that has its own mainline. That doesn't stress me out at all. Whereas my brief and traumatic experience with Rails was something where I felt like it was actually kind of a big deal to make another Rails application and having many of them going concurrently. I know that maybe there's not a great reason for it, but for some reason it just felt all wrong. With Go, it doesn't. I think that's something to do with just the philosophy of the system, and everything seems pretty simple. The standard library is readable, and so on and so forth. I think that out-of-the-box performance in Go is also a huge breath of fresh air if you're coming from Node or Rails or Python or something like that. It still leaves something to be desired, and I'll talk about that later, and I think it does come into play particularly with large fan-out systems, but in general, I'm really pleased with the performance. So I think it's also really important in a distributed system, and I'll talk about this a little bit more, if it's big enough, you're going to have enough people working on it that you didn't write all the code, and so you need to be able to hopefully edit multiple layers of the stack, and I think it's equally really important to be able to do that without bothering other teams. If you want to send them a small review that touches some of their code in your company, you should be able to do that confidently. And I think that static typing and what Go has done here is invaluable. This is not news, I think, and this is why I think a lot of people I had to do a huge refactor last summer when we made some significant changes to our product, which is all the backend is written in Go. And it was actually almost joyful to just change a bunch of types and fix compile errors. And when that was done, it was kind of working. It was really remarkable. And I think that's a testament to Go, that was a fairly pleasant process. The compile times, of course, are also a huge improvement over some other statically typed languages. But again, this is nothing new, and I'm not going to dwell on stuff that's been well covered already. Another thing I like about Go, Go routines make it really beautiful, actually, to handle things like flow control, even multi-tiered flow control, and pushing back instead of just running out of memory and crashing is also really elegant in Go, and is something that I was talking to someone just before the talk about how they were able to replace 3 levels of complexity with a single Go service that replaced, I think it was replacing some sort of Nginx thing and another load balancer and a service, all just got replaced by one Go binary that had no trouble with the performance, and when it's running out of resources, just 500s instead of crashes, which is what you want. I'll share these slides if anyone cares, but I linked to a deck where people describe this piece of it in more detail. Now we're getting into areas where I think Go is not doing quite as well. Debuggability I'll talk a lot more about later in this talk, but I think it's actually an area of significant weakness for Go, especially when you're talking about really big systems, and I'll talk more about that later. And this has nothing to do with Go, but I'm kind of feel like as long as I have the opportunity to talk to people, I want to reiterate how important I think it is for inter-process communication to be done in a way that's self-documenting. And that's sort of code for saying I think using protobufs or Thrift or something like that, or Avro or whatever, is really important. I think JSON makes sense when you need to build an API for people outside of your company and you want to make sure that they can get started quickly with your product. But I think that building JSON APIs or similar things like that require kind of code comments to document how they work is sort of a bad idea in the long term. I think that the maintenance issues there are significant. I think also that the serialization, deserialization, and a high throughput service can become significant. And I'm a really firm believer in trying to be a little bit more formal about it. And somehow this makes me feel like there's an analogy between JSON and JavaScript and like protobufs or Thrift and Go, in the sense that you have a little bit more typing, but it actually, I think, saves you time in the long run in terms of sort of maintenance headaches and compatibility issues. All right, so this is a slide that I stole pretty shamelessly from a deck that Jeff Dean and Luis Barroso presented from at Berkeley. It's a really great presentation. It goes into a lot more detail about kind of performance tricks in distributed systems and trade-offs between throughput and latency that are made at Google. And I was actually surprised that they published it. I thought it revealed a bunch of kind of heuristic things that I didn't think they would talk about publicly. So it's a great presentation. I really just wanted to steal this. I didn't feel like trying to do this in Google presentations. So basically, this is just a diagram of what I think is a pretty typical serving system. You have a query coming into some kind of top-level front end. In this situation, the front end has some ad system it sends things off to, and it also sends to what Google calls the super root, which is just this kind of like, it's this process that takes all the different things that can be combined into Google search results and merges them and ranks them. And then each one of these things is like a multi-tiered, sharded, cloned system. And I can say, I think without revealing anything too surprising, that like a cache miss at Google search will often hit like thousands or even tens of thousands of processes before it gets back to the user within whatever fraction of a second that takes. And so this is a really highly tuned system, and they're very, very sensitive to latency. The nodes here, I think it's worth saying that these aren't replicas, these are different shards. So you have some corpus that's too large to fit on one machine, so you split it into pieces. Each one of these pieces is also replicated for load balancing, and that's not pictured here. I talked about this already. I think it's also important to say that when you see companies growing, and of course Google is larger than most of the companies that we work at, but even at a medium-sized company, I think you start seeing this thing when you get about 100 people or so, where the systems start to be complicated enough that you don't know how they work. Like, you can't know how they all work. No one at the company knows how everything works. And you have these communication issues that come into play as well. And this is, again, an area where I think Go, it really shines compared to something like Rails. I mean, I think part of the reason that Twitter had trouble really making significant product changes for several years was because they were trying to get themselves out of that mode where they'd gotten themselves with Rails into a scheme where it was easier to make changes confidently. And I mean, that's just my opinion from talking with people I know who work there, but I do think that it's a really significant cost. Like, the communication cost of code is a huge deal, and when you start scaling out is maybe even a bigger deal than the cost of implementing things. Like, being able to understand things and change things quickly, I think is really important. And Go, I think, is a great step from a lot of the other kind of popular languages people are using to build stuff quickly these days. I'm going to move into kind of talking about latency, which will be the next section of this talk, and I'll get a little bit more detailed now. I should have said this earlier, but if people have any questions or if I'm going too quickly, just please interrupt me or raise your hand. I'd welcome that. I did actually draw this myself, unlike that chart I stole earlier. This is a pretty straightforward chart, like a latency distribution. I see a lot of things, like I know that New Relic recently introduced 95th percentile latency, which I'm glad they've done that, but I think be suspicious of people who talk about average latency. It's rarely important. If you're talking about a system that other things depend on, or if it's sharded out, this red area is what you really care about. And even if you have a really beautiful, like tight little distribution close to low latency requests, so you have most of the requests are being serviced very quickly, if you have bumps over here, this is a big deal. And this is an area where I think Go right now actually has some problems. I also think it's an area where Go is naturally going to improve, especially past 1.5, I think. Reading their documentation about what they're planning on doing, I have some high hopes for it. But the key observation is that if you have a service that has one component in it, this is actually not a big deal. It's like if 1% of your requests take wildly longer than everything else. They take orders of magnitude longer than the 99% of requests. That's okay if there's only one of those, but it's just the kind of birthday paradox thing. As you add machines into that picture, if there are 100 processes in your system and 1% of them are really slow, 63% of your requests are going to hit one of those machines. And so things like garbage collection hiccups can become a really big deal if you have to spread them out across distributed systems with lots of components. And if you're not willing to just time out and you have to return the results from that process, it's even more of an issue. I also drew this. This is my crowning achievement in this presentation. It's all downhill from here in terms of graphics. I hope this makes sense. This is, I'm going to talk a little bit about distributed tracing in a bit, and this is how Dapr, which is Google's distributed tracing system, and how Zipkin, which is the one that Twitter open sourced recently, this is roughly how they visualize these things. So you should see this thing at the top, this bar, is one request. Like, let's say it's one user-facing request. And each of these things that it directly calls into are systems it depends on and makes, let's say it's making RPCs to these systems. And as we're flowing across, you can see, time is obviously extending. And the key observation here is that this is a very, very typical shape for a distributed trace, at least in my experience of looking at them in common distributed systems. You have some fan out where you have these three backends. You process them mostly in parallel. Maybe there's a little bit of latency between these various requests going out. But this top request, let's imagine that it makes these three requests in a pretty short order, and now it's just waiting until they all come back before it can make this final request. So perhaps like this is an insert into a cache service or Redis or something like that. So the bulk of the request, your process is just sitting there not doing anything, this top level process, waiting for its backends. And its backends return in sort of similar fashion. They have their own backends, and they return as soon as they're all done. But you have this one guy here. Let's say that this one was having a queuing issue or was having a hiccup from garbage collection. This single request slows things down substantially. Because I couldn't fit it, there's only 5 of these, but it really is not uncommon for this to be more like 20 or 50 or 100 in some cases, and that can become a really big problem. So these are the things that end up slowing stuff down. We did an analysis while I was at Google using some of the Dapr data across the entire company and looked for critical paths on web search. So the critical path, of course, is just to refresh people's memory, is just every process that was actually holding up the main request. So you can see that these guys aren't, like they finished in time and there was loads of time before this guy finished, so it's not an issue. So the critical path is something that we're incredibly interested in, and ultimately that's what you need to optimize if you want the end user query to come back quickly. And what you end up seeing almost invariably is that slow requests are due to 1 or maybe 2 requests, like underneath the top level thing that we're trying to satisfy, that took too long or took way longer than their peers. And this is what latency ends up, like latency analysis in distributed systems ends up being focused on finding and eliminating these. It's not really on making this any faster. If these guys are your problem, you're in really good shape. It's these ones that you have to worry about. Does that make sense? People listening? Okay. Okay, so back to Go. So garbage collection is something I think I'm a little nervous about. I talked about a bunch of things about Go that I think are great. I'm not dwelling on those because I think that the Go team has done a really good job explaining what's so great about Go. But there are areas that I think do require a little bit more attention. I have to admit that my use of Go in production has been post-Google, and I haven't really been able to push it as hard as we push things at Google. I've never run into an issue with GC that felt material. Like we've seen little blips, but it's not a huge thing. I'm positive if we end up with systems that had hundreds of components, that it would definitely be a thing. I mean, maybe not a big thing, but it would be a thing. And I'm pretty distressed by the current implementation for the GC and Go. I'm also pretty encouraged by what they're planning to do about it. I think that their focus is just right. They've had to choose a heuristic. I mean, GC is a very difficult thing to do. Either you do what Java does, and you have some like insane number of parameters you expose to people, and it becomes this sort of configuration nightmare, or you just sort of take a guess at what an appropriate configuration is for people. And I think they're kind of erring on that side of the spectrum right now, which I'm actually happy about because that Java thing makes me totally crazy. But I am a little bit concerned that like if anyone's trying to build something that's super real time, they're going to run into issues. Their plan of record is, and if anyone has better information, please correct me, but my understanding is that their plan is to get to a point with Go 1.5 or even with Go 1.4 where the stop the world garbage collection will only happen for 10 milliseconds at a time out of every 50 millisecond block. So basically, it'll stop the world, take 10 milliseconds, do as much as it can. If it's done, great. If it's not done, spend the next 40 milliseconds probably doing concurrent garbage collection in a less efficient way at the expense of throughput, but giving latency a break. And I think their assumption is that 10 milliseconds is never going to kind of break the bank for anybody in terms of latency. Certainly nothing like some of these like kind of nightmare scenarios where your process stops for 5 seconds while the garbage collector goes and does its thing. So I am hopeful about that. The other good news about this, I guess, is that even if this is an issue, it's not impossible to program around this. You can make multiple requests to clones and just cancel the one that comes back second, or you can build your own allocator basically with free pools, which is really agonizing, but definitely an option and something that people can pursue. And I am optimistic about where this is going, although I don't think it's quite there yet. And if I was in charge of a company that was building some really high throughput, low latency system, I would be a little nervous about this right now. So yeah. Sometimes there are thousands of processes involved in a request, or even hundreds. It becomes an issue. And I think another thing that people don't talk enough about with distributed systems, but I think invariably becomes an issue once the systems become sufficiently complicated, is that you cannot understand what's happening in them. Just by looking at logs, and certainly by looking at the code. Like you'll have a request that takes too long, or you'll see some kind of strange error, and there's almost no way to figure out what happened. I think the reason why that becomes a problem is that vanilla logging, where you're just logging to a local disk, or maybe you're logging to local disk and then using Papertrail or Loggly or something like that to aggregate the logs, is not that effective in highly concurrent systems, because either you do the thing where you only log significant surprising events like errors, which is fine, but then like everyday requests you have no information, or you do fine-grained logging per request, and you end up in the situation where either your logging becomes like materially expensive and or you have so much interference. If you're handling in Go, which does concurrent processing really beautifully and easily, if you're processing 100 requests concurrently and they're all logging concurrently, if you're looking at that log file, it's kind of madness to try to understand what's actually happening because of all the interference from different Go routines or different subroutines of things. Does that make sense, I think? So it gets even worse if you then make this, instead of just debugging a concurrent system on one machine or in one process, you're now debugging a concurrent system across many machines. And this is the situation that you find yourself in if you're building like a high throughput, low latency system. You end up it's foolish, I think, to try and actually figure out what happened. If you have 100 processes that are all doing concurrent work, and you're trying to figure out why one request went awry, you're in big trouble. And so this is why distributed tracing systems become an issue once companies get to a certain scale and once products get to a certain scale, is that you need to have some way of figuring out on a per request basis, not just for one process, but across processes, what happened. You just want to know, like, you want to have a basic log of just the usual stuff you would log to like a V1 type fine log. And you also want to know basic timing information. When did a request come in? When did it go out? When did it finish? That sort of stuff. And I think that this is an area, and this is the nugget that I'm hoping to convey tonight, that I think Go has a significant problem. I actually don't know how to do this in Go. And if anyone does, I'd love to talk to you afterwards. I think it's a pretty interesting thing. So a distributed trace is a log of concurrent activities. So things that are happening at the same time. And I think people who've used Go have probably read all the concurrency versus parallelism stuff. In this case, they're probably concurrent and parallel. If they're happening in multiple processes, it doesn't matter. The point is that they're just happening concurrently. and that you're also integrating them from many places, and that's the distributed nature. In order to do this well, at least based on my experience working on Dapper and from what I've learned in my own career anyway, is that you need to have control over the wire protocol. That's no problem for Go. And you need to have no code footprint and vanilla function calls. So if I call a function, it's not reasonable to ask a developer to instrument every single function call in their application just so distributed tracing works. It's one of those things that you don't want to care about at all until you need it, and then you want it just to work. And if it requires a huge amount of developer overhead, it's not going to happen, especially across teams and across SDKs and across APIs and stuff like that. It's just not going to happen. So it needs to work transparently across function calls. And it also needs some way of integrating with execution queues. So the kind of runnable stuff in Java and C and C++. I don't know if there's as much of a convention at Google. We had this callback and closure system, but I think you're all familiar with the pattern. You have some sort of queue. You put asynchronous work into the queue. That's another area where distributed tracing needs to be pretty seamless. You want to make sure that when if you put something into a queue and then it goes through the queue and it comes out, you need to make sure that the trace knows that's still part of the same logical request. So you need to be able to instrument that. These are the three things that are really important. If you can do these three things, the rest of it's really not that hard. The rest of it's just like building a pretty straightforward collection system and building a GUI around it. But these three things are not to be negotiated around, really. So what this boils down to is custom code in RPC systems. You rely heavily on thread local variables to avoid instrumentation, avoid additional code overhead in function calls. And then you need some kind of special runnable implementation. And I'm using the Java terminology here, but whatever the work item you put into your queue, you need some way of instrumenting that so that you can find out when it starts running later and have your own tracing code called into play. The first one's fine. The last two are a huge problem in Go, especially the thread locals. So in Go, as it stands now, the only way I can imagine this working is if they added something that is thread locals or is akin to thread locals. So going back to this slide or something like this, if in the super root I want to call upon client libraries that talk to, in this diagram, images and local news and web and stuff like that. I didn't write those client libraries. When I call them, it's not reasonable for me to assume that they have added something for like, put in your trace context here. You want that just to happen automatically. And in Go, they seem pretty dead set about keeping Go routines super, super lightweight, which means they seem pretty dead set about not adding thread local stuff. But then again, I don't know how you would debug systems of this scale or even an order of magnitude simpler than this scale without something that allows you to connect the dots across processes. And again, I think that this is something that Go has some real work to handle, some real work to do. And then similarly, if you have a channel, which is, I think, a beautiful concept in Go and really well implemented, since they've put that into the language itself, that is the execution queue of choice in Go. And anyone who wants to build a queuing system hopefully is going to use channels to do it. And I think that this is another issue where you can't just insert things into a channel and expect it to do the right stuff with tracing. To do this right, I didn't think I had time to really go into what I think the proposal would be, but you need different parameters when you create a channel somehow. You need to have some way to parameterize it to say, I want you to keep track of thread locals or tracing information, or give me a chance to have a callback before something is enqueued into a channel and when it's dequeued from a channel. And I am amused sometimes by the Go team. I kind of like them personally. I know some of them from Google, but they're very principled about what they're trying to do. This to me sounds like the kind of thing they would hate. Like it just sounds like the kind of thing they would never do. And I'm wondering if they eventually will, or if this is just going to be this gap. But right now, if you build a Go process and it's in the middle of the system and it's not at the lowest level, I don't know how you can figure out how the stuff that's coming in is connected to the stuff coming out in a generalized way that would work across APIs. So yeah, I hope I didn't go too fast. Am I about right? I'm about right. That's wonderful. So I think that Go is pretty well positioned to address almost everything about distributed systems that I care about. I love the language. I plan to use it for everything until something better comes out. And I think that the latency issue is presently may be a problem. I think by the end of next year, I can't imagine it's going to be a serious issue if they do what they're saying they're going to do. Right now, I think it might be slightly a problem. And then I do have this significant grievance about debugging. My hope is that eventually it really will be a problem and that they'll fix it. Until then, I'm concerned about this, and I think this actually will be kind of a blocker for a certain type of analysis that is actually really essential once you get to a certain scale. But until then, I'm excited to use Go, and I really enjoy it. So I think that's pretty much the end of my slides. I'm happy to take questions at this point about any of this or something else or anything people want to ask. Great, I'll be here for 2 hours. I'll tell.
Well, I guess I have an idea.
Great.
What about doing something similar to what they did with Go Cover and using a program that instead of using Go Build to build your program, you use something that decorates your code with debugging. It can add fields to structs, it can add parameters to functions, and you could use that to, at least within a single binary, get debugging information from beginning to end.
Yeah, that's an interesting idea. Did people hear the suggestion in the back? So the suggestion was to use a tool that structurally is similar to Go Cover, and that it runs over the binary you're trying to build and inserts instrumentation like the instrumentation I'm talking about where it's needed. I think that's a really interesting idea. I think in a situation where you could actually get pretty much everything done automatically, I think that would work. In practice, to make the distributed tracing function correctly, you always end up needing a certain amount of hand tuning to, like there will be some situation where it shouldn't be traced and it was traced. Like a situation we have at Google sometimes is that a request would come in, the very first request would come in a process, and while it was handling it, a bunch of lazily created structures would be created. And those things would make millions of RPCs over their lifetime. And they'd all be considered part of that initial trace. So you'll have to do things where you'll cut stuff out of the trace. And that sort of thing, I think, would be kind of odd to have those APIs in place, but also require this separate build process. But I think it's an interesting idea, and I think could definitely help with a lot of it. It basically is like, I think that's akin to saying it's almost like having a compiler flag. It's almost like, when you compile this, I want it to be something else. Another thing I should have said about distributed tracing is that it needs to be running all the time in production. It's not something that you turn on for your binary and you push a debug binary to production. It needs to work all the time and have no overhead that's perceptible. And I think that could, that could cause people to forget about this or something. Ideally, it's something that people don't need to remember. I could imagine a company policy where you say you have to compile everything here like this, but ideally, it's something that's just on. I think, yeah. But that's a good suggestion. That's a great question. So the question was, do you trace everything that comes in, or do you sample some? And so the answer is sort of a little of both. You sample everything, and you keep. So basically, I didn't have time to go into a detailed description of how it works, but the summary is that every time a new request is starting at the top of the tree, you basically pick a random 64-bit number and call that the ID for the trace. And then as the request propagates across the distributed system, you pass that ID along with it, and you log stuff locally not over the network, and certainly not as part of the response, but you log things locally attached to that ID if it's been traced. You always pass the IDs around, so you do that no matter what, but you only do the logging if a coin has been flipped and you've decided this trace is going to be sampled. And so one of the big problems is how do you want to weight that coin? Do you want to weight it equally and just do it uniformly? At Google, the default is 1 in every 1,024 requests is traced by default, but then for lower throughput systems, they'll bump it up to 1 for 1 or 1 for 16 or whatever. In some situations, you'll want to be smarter about it and say, oh, this request is going to be interesting because it has a certain pattern match to it, and so I'm going to turn on tracing after the fact, and you can do that as well. But you trace everything, but you only log a fraction of it, because the expensive part is really that logging, and the I/O you have to handle for the logging is the expensive part. It's a great question, though.
Hello. Okay. So A chart earlier on that was something I've personally felt pain, the latency one in the critical path.
This
Yeah,
one?
so, I mean, this is a very common problem. So it's great to see this. What I want to know is how have you actually fixed these problems? In my experience, you're lucky if it's an outlier machine. You go in and you try and find out what's wrong with that machine, but that's if you're lucky. The only answer I've really had is you measure everything so that when it does happen, you can try and work out. Can you speak to
Some of the
what really
techniques.
matters? How do you start to debug these issues?
Yeah, sure. So yeah, these are really thorny problems, and I think one thing you do is you build an ad system that's like just printing money, and then you can hire a lot of people to work on it. I mean, I think that's what Google did. But if barring that, I think another thing you can do, and actually that talk I was referring to, this Jeff Dean talk, goes into a lot of the specific techniques that you know that they've used at Google to get around this issue. When it's, I mean, obviously, if someone's doing something stupid, you fix it. I mean, but that's not the interesting one. Typically, what you end up doing is you will, if you can't work around it otherwise, you'll do something where you send the request to multiple. So instead of just having these different shards, you might have two clones that actually have the same data. You send it to both, and you accept the fact that you're using extra resources, and then cancel the one that doesn't come back first. And it's incredibly expensive and it's incredibly painful, but it works great because you're doing a great deal to reduce the chance that both of these clones are going to run into that problem. So that's like one of the techniques they use. Yeah, I think that's true, especially when you try to be careful about using your resources. I mean, the other thing you can do, and this is sort of obvious, is just to reduce interference and move things off of shared systems and create a more controlled environment. But that's pretty painful and really expensive. But that's something that a lot of projects would do with their highest value systems. They would just basically over-provision the system, which is depressing, but they would do it. Yeah. Yeah, the question was, if you're sampling and logging 1 out of 1,000 requests, how does it actually end up somewhere where you can do something with it? Is that a fair paraphrase? So, well, with Dapper, after that there's additional sampling. 1/10 of those requests would get centralized into Bigtable, which is sort of like Cassandra, just like a big distributed key value store. And so you could run MapReduces and things like that over that data and do really detailed aggregate analysis. But most of the data just stayed on disk. And we had a system we had a daemon that was actually, it was the scariest thing I ever did at Google for sure, is running a daemon that ran as root and ran on every machine at Google. And that's what this was. So it has really, really strict resource restrictions that it imposes on itself, and it sits there and opens a port to the world and basically serves up this log data. And just anytime you ask for a request, you give it a time range. It'll binary search the logs to find that range, look for the request you're asking for, and return it. And that happens at interactive speed. So you could just basically you could resuscitate the trace just by visiting all of the actual machines involved, as long as you got there within about a week. After a week, the data would typically get reclaimed as log rotation took place. But that was actually commonly how it was done. So you just build a process to serve it. If I were to do it again, I wouldn't do it that way. When we built it, Google's network wasn't as good as it is now. And I think that networks in general have gotten so much faster over the last 5 years or so, it probably would make more sense just to log the stuff of the network to some central place initially and skip this additional complexity of having the data distributed across your entire fleet of machines. But that's how we did it at the time.
So you talked about a case like the one up on the screen right now, where you can basically decompose the problem to find the offending process or shard. Are there any situations where it's not this obvious, and where it might be the interactions between processes or between shards or between systems?
Unfortunately, yes. Yeah, I think that there are a lot of situations where it's not this obvious. I mean, the question was, this is a pretty brain dead example. Like anyone could look at this, and if you understand what it's saying, you can understand what the problem is. And the question is, are there things that are a lot more subtle that would be responsible? Are you saying, are there things that are more subtle that explain this behavior than like a GC hiccup? Or are you saying there are things that where it doesn't have this weird shape to it, it just takes too long in general?
Well, for example, it may be if you were to isolate a subset of these shards or processes, they would perform fine, but when you put them together, then they suddenly don't perform in the additive way that you might expect.
Yeah, I mean, that definitely, I've seen that happen. The types of, let me think if I can think of a good example. I mean, there have been situations where it's often that you depend on some sort of backend that wasn't provisioned correctly, and you spin up a system that has, tens of thousands of processes in it, and this dependency, which is fine when you're testing it at a smaller scale, becomes a serious problem, and then everything kind of grinds to a halt. And I feel like that pattern is actually responsible for more of Google's like user visible outages than most things I can think of. It's a difficult one to catch in staging, and it's a difficult one to recover from quickly in production as well. So that's one type of situation. And oftentimes it's like a hot shard, like if it's a big table or something like that where you have some big distributed store and all these different pieces are simultaneously doing their part of the job, and then maybe this one piece has some picture in it that ends up becoming a viral internet success, and you have too much attention being given to it. If you haven't built good caching infrastructure on top of that, you can end up with just a hotspot, and those things are notoriously difficult to predict and to fix as well. Yeah. So the question is, if I'm so eager to trace Go programs, what information do I want to get out of it? Is that basically it? The main thing I want by far in a distributed system is just the RPCs. I just want to know when the request came in, when it went out, and when it came back, and when you returned to your parent in the tree. That's the main thing I want to know by far. And I also would like to know how much of that time was spent over the network and how much of the time in an outstanding RPC was spent actually in the server. Because something like this, I didn't want to draw it in here, but in the implementation at Google, each one of these bars will have a breakdown of how much the time was network time on the client side, how much was network time on the way back, and how much was actual processing time. And so you can discover that these services aren't located close enough. The latency dependency is such that they need to be physically closer so that those network latencies get turned down. So the RPC information is the most important thing, probably by an order of magnitude. And then second to that, I think it's really important just to kind of log basic features of the request, because if you end up with an outlier, you want to understand why is this an outlier? Like what is it about this request that's so expensive? And so often logging that type of stuff. I almost treat the RPCs just as the function calls in a distributed system. So the type of stuff you would want to log at the top of a function is the type of stuff I'd want to see for each RPC that goes to the system. Yeah. Can you speak up? I'm sorry. That's a really good question. So the question is, do you just use the system clock when you're doing these sorts of timing diagrams, or what? Well, you should definitely run NTP. That helps a lot, and it'll kind of get you within a few milliseconds of reality. I think for most systems right now, that's enough to get you where you need to be. If you need to have sub-millisecond fidelity on these things, then I think you need to use a different system than the one that I built. But Spanner they published this paper a year or two ago, I don't remember, that has a really interesting distributed clock section to it. And I think you could do something like that and have more fidelity about the specific sequencing of events, which is almost more important than what the actual times were. but it would probably be pretty expensive as well. But yeah, I think NTP gets you most of the way. I love NTP.
Thank you.
Yes.
Appreciate that. So round of applause.